وبركاته. طلاب المرحلة الرابعة إن شاء الله زينين. محاضرتنا لهذا اليوم طلاب المرحلة الرابعة Functional Analysis. محاضرتنا نكمل المحاضرات السابقة. محاضرتنا Orthonormal Sequence. We take more theorems and maybe examples. Theorem. Now we take this theorem. Let V, this is another product, be a Hilbert space S is equal to phi I such that I belongs to index I. This is said an orthonormal system. Orthonormal system for V, and alpha I belongs to natural number n, a sequence this is a sequence of complex number, a sequence of complex numbers. Then summation I is equal 1 to infinity alpha I phi I converges if and only if summation I from 1 to infinity absolute value alpha I, this is square, less than infinity. That means this is converges. If this sequence converges, then this sequence also will be converges if and only if both sides. In this case, we also have norm of summation I from 1 to infinity alpha I phi I. This is norm is equal to under root summation I from 1 to infinity absolute value alpha I square. Now we try to prove this theorem. Prove by this direction. Now first start with this direction. Let summation I equal 1 to infinity alpha I phi I be convergent. Then the sequence of partial sums Sm, n belongs to natural number n, with Sm is equal to summation I from 1 to m alpha I phi I is convergent sequence, is convergent sequence. If this sequence convergent summation alpha I phi I من from 1 to infinity, if this is sequence convergent, then the partial sums of this sequence, let's call it Sm belongs to infinity, partial sum, that means not all these terms, just m terms from the sequence will be also convergent. This is page number 1. And but every convergent sequence is a Cauchy sequence. Is a Cauchy sequence. We know this is from mathematical analysis. Every convergent sequence is a Cauchy sequence. Since V inner product is a Hilbert space, is Hilbert, that mean V with inner product is complete by definition of Hilbert space, and therefore there exists a psi belongs to V such that there exists a psi belongs to V such that Sm, this is sequence Sm, convergent to a psi as m goes to infinity, i.e. because this is Hilbert space is complete, so there is a psi belongs to V such that this sequence Sm, this sequence convergent to a psi. that mean a psi is equal to summation I from 1 to infinity psi to m, psi to m alpha I phi I, this is equal to psi. This implies summation I from 1 to m alpha I phi I, this is equal norm of psi, and this is less than infinity, and this is less than infinity. On the other side, the generalized Pythagorean formula Pythagorean formula gives summation norm of summation I from 1 to m alpha I phi I, this is square, is equal to summation I from 1 to m alpha phi I alpha I phi I square, and this is equal to summation I from 1 to m this is by definition of alpha, by definition of norm, this is alpha I square out of norm, and this is phi I square, I from 1 to m, and this is will be equal to 1 I equal to 1, because this is orthonormal system. So this is will be equal to summation I from 1 to m alpha I, absolute value alpha I square. That is summation I from 1 to m alpha I phi I, this is norm, is equal to root of summation I from 1 to m absolute value alpha I square. We take root from this and this, so root, we take this, and you see in our theorem, in this case we say, in this case we also have summation this is equal to root of this. Hence we have summation I from 1 to m alpha I square is equal to norm of summation I is equal 1 to m alpha I phi I, this is square. Also, of course, this is less than or equal norm of summation I from 1 to infinity alpha I phi I, this is square, and this is less than infinity. This is less than infinity. Why this is less than infinity? Because we assume that this is convergence at the beginning. Proof assume this is be convergence, so this is will be less than infinity. This is page number 2. Taking m in this equation, inequality, taking m goes to infinity in above inequality, this is inequality, we obtain norm of summation I is equal 1 to infinity alpha I phi I is equal to root of summation I from 1 to infinity alpha I square. That what we need in our theorem. Look, this is in our theorem, this is goes to until infinity, and this is until infinity, so we get it now. This is equal to this. This is first direction. Now second direction, prove the second direction. The second direction, let summation I equal 1 to infinity alpha I square this less than infinity. Other side, we assume that this is less than infinity. This implies that the sequence of partial sums are n belongs to natural number n, with Rn is equal to summation I from 1 to n alpha I square. This is partial sum. Its convergence sequence is convergent sequence in R, real number. Hence Rn, n belongs to natural number n, Rn is Cauchy in R. Are complete. Of course, are complete. This implies that there exists R belongs to natural number R with R is the greater R, capital R is the greater than 0, such that summation I from 1 to infinity absolute value alpha I square is equal to R. Sorry, R, this is number, not real number. This is positive number, this is R. And using this is 1, use this is 1, in our theorem. In this case we have this, let's make it this star, this is equality star, and using star, now using star, this is star, we mean this is star, use this, we get norm summation I from 1 to infinity alpha I phi I is equal to root of R, because this is equal R and you put here R, so this is equal to root of R, and this of course less than infinity, and this is finish proof of our theorem. This is page number 3. Now we move to other remark. I have a remark here. Maybe you already noticed that the element of an orthonormal system can be seen as elements of a sequence phi n belongs to natural number n of orthogonal vectors such that norm of phi n is equal to 1 for all n belongs to natural number n. We call such a sequence an orthonormal sequence of vectors in the inner product V. Now we take this theorem. I have theorem now. Orthonormal sequence are weakly convergent to 0. Moreover, they are bounded. Look, this theorem, orthonormal sequence are weakly convergent to 0. Any orthonormal sequence are weakly convergent to 0. Moreover, they are bounded. Moreover, they are bounded. Here sequences, some orthonormal sequences are weakly convergent to 0. Moreover, they are bounded. Proof. Let phi n belongs to natural number n, be an orthonormal sequence in V inner product V. Now what we must show that phi n converges weakly, this symbol of converges weakly, to 0. 0, this is vector in V, i.e. that mean absolute value phi n with phi inner product minus 0, this is converges to 0 as n goes to infinity for all phi belongs to V. This is page number 4. Now we have to prove this. Absolute value of inner product phi and phi minus 0 converges to 0 as n goes to infinity for any phi belongs to V. If we prove this, that means phi n is weakly convergent to 0. Weakly convergent to 0. Now we need to use Bessel inequality from the Bessel inequality. We take it previous lecture. We took it summation from n from 1 to infinity. Absolute value 5 phi n square less than or equal to phi square. This is from Bessel inequality, and this is less than infinity. Is for all phi belongs to V, and this implies from Bessel inequality summation n from 1 to infinity. This is series phi n square what converges, because this is less than what, less than infinity. At this point note that absolute value inner product phi n phi square is equal to phi n inner product, just replace, and this is less than or equal to summation n from 1 to infinity alpha phi n square, and this less than, and this less than epsilon. This is less than epsilon for all n is greater than capital N. This is maybe take here k from k, n equal k to infinity. This is convergent series can be made arbitrary small by choosing n sufficient large. Choose n sufficient large. We see that this less than epsilon, and if this is less than epsilon, boundedness follows from the last above theorem. Sorry, not above theorem. In the other theorem, in the theorem, in the last theorem, in the section strong and weak convergence. This is theorem. Weak and strong and weak convergence. If this less than epsilon, so this is will be bounded. Remark: is it possible that orthonormal sequence sequences are strongly convergent? This is a question. Is it possible that orthonormal sequences are strongly convergent? Strongly convergent to zero v. Is this is possible? Strongly convergent? The answer is no. Since phi n is equal to 1 for all n belongs to natural number n. So this is clear. Look about, I repeat this theorem, proof of this theorem. Orthonormal sequence are weakly convergent to 0 wherever they are bounded. Let phi n be an orthonormal sequence in V inner product. We must show that phi n converges weakly. This is mean that phi n phi minus 0 converges to 0 as n goes to infinity for all V. So we get this from Bessel inequality summation phi n square n from 1 to infinity less than or equal to phi norm phi square. This is less than infinity for all phi n. So that means this is convergence this is series is convergence. At this point, note that, and look, this phi n phi will be equal to phi n, and this less than 2 equal make take n large enough equal k to infinity phi n square. Of course, this will be less than this, and this less than epsilon, because this is convergence. So this is less than epsilon equal for all n. That mean we prove that mean this will be less than epsilon. That if take epsilon goes to 0, so this is goes to 0. What we need here, and here 0, here put here 0, and this is root will be, if we take root, will be all just stays phi n minus 0 goes to 0 if epsilon goes to 0. And boundedness, this is the first one, and they are bounded. Boundedness follows from last theorem in the section of strongly and weakly convergence. The last theorem in the section strong and weak convergence implies this will be bounded. About this remark, is it possible orthonormal sequence are strongly convergent to 0? Will be 0? The answer is no. The answer is no, because phi n, norm of phi n equal 1. So this impossible goes to 0 for all n. I think this enough for today, and this will be page number 5. Thank you very much.